So in this video, what I've done is I'm continuing from the previous video. This is the last. This is all the examples we did last time. In this video, what I want to do is basically show you what would have happened if we had not made the choice as here. So you may ask, for instance, if instead of, I mean, you always have a choice. You don't have to let u equal x. We could have let u equal sine x. So here I want to show you what would happen, for instance, in this example, if we let u equal sine x. Can we actually get an answer? Does it actually work? Or does it make the situation worse? So that would mean that this would be the substitution. So we would say let u equal sine x, and if we did that, that would leave then dv be x dx. And there's no other choice other than this. So now if I differentiate du, this gives me cos x dx, which is not a major problem. Here, on the other hand, when I integrate both sides, I end up with x squared over 2. Now, if you see that, the integral, remember, you're always looking at this integral at the end, this integral, v du. So let's, just for the sake of argument, let us just go ahead with the integration and see what happens. So uv is going to be x squared over 2 sine x, that is not a problem, minus the integral of v du. So v is x squared over 2, and du is cos x dx. So now, as you can see, we've not actually simplified the resulting integral, we've actually made it more complicated. So the cos x and sin x is not really a complication, they're just basically like each other. However, instead of x here, we've got basically x squared over 2. So instead of x here, we've got x squared over 2. So it's gotten more complicated. So obviously this will therefore be a failed strategy. It will not achieve what we want to achieve. So I just wanted to show that it is possible for integration by parts to go wrong. It all depends on the choice of what you choose to differentiate and what you choose to integrate. So what is u and what is dv is extremely important in the integration by parts. And you cannot use a method. There is no method to this, because I'll show you another example. So what I want to do is show you another example, a slight variation of this, just to show you that sometimes it's better, as I've said in the previous videos, the methods, there are no real methods to integration. They're just techniques. So you have to do it on the basis of experience, and the more questions you solve, the better you get at integration. So here, this example demonstrates. Now, if you remember, we had the previous example that we had here that we did earlier, where okay, so I brought this example back here for you, just parts of it. So x squared cos x, and if you remember, we let u equal x squared and dv equals cos x, and we got 2x dx and sine x, and and it was working fine. It was reducing. Now this would tell you that maybe the technique is that if I have this kind of a product here, then maybe I should let u equal x squared and dv equals ln x. It may work, and it will work, but it is the longer way of doing things. So for instance, I'll show you that here, if we were to choose u equals x, see what actually transpires. So this becomes x cubed over 3. And now if I put the integral back together, so I get x squared ln x dx equals uv, so it's going to be x cubed over 3 ln x minus integral v du. So v du, so v is x cubed over 3, and du is 1 over x dx. So I end up with this, and of course we can clearly see that the x cancels with this, leaves a 2 here, so we end up with x cubed over 3 ln x minus the integral of the 1/3 goes outside, x squared dx. Very simple integral to do, of course, and we end up with our final answer, which is 1/9 x cubed plus a constant. So very easily done, piece of cake, simple. Now, but look, what I did was I did not use u equal x squared. Let's try to see what happens if we actually do that. So what I'm trying to say is let's look at this, and we'll do this in red now, where if we were to proceed in a different direction and say let u equal x squared, and that means that dv is equal to ln x dx, then of course we would get du is 2x dx, and v, based on the integral we have over here, is just going to be, of course, x ln x minus x. Okay, and that's based on this integral, this result that we have here. Okay, so now if I put them together, so that means I'll have the integral of x squared ln x dx is equal to uv, so that's going to be x in fact cubed into ln x minus 1 minus the integral of v du. So v is now, remember, x into ln x minus 1 multiplied by 2x. So multiplied by 2x dx. So you can see the situation is getting more and more complicated. The integral is not simplifying, in fact, and we end up with basically the 2 goes outside, the x goes in, and you get x squared ln x. Okay, and you're going to get minus x squared ln x minus 2x squared. The 2 is outside, so x squared dx. This is after opening the brackets. So as you can see, now we have the x squared ln x over here, and that's what we started with in the first place, and the minus x squared. Things don't seem to be getting much better. However, a little trick can solve this one and shorten the answer a little bit, and I'll show you what that trick is here, which we will also be using in another well-known integral where that trick works. So if you notice in this particular integral, if you notice, we have this integral here, and it's minus 2x squared ln x dx. That's what we have on the other side, you can see here. So what I can do is the following. I can rewrite the integral as is, I'm going to keep this x squared. So what I'm saying is basically I have this x squared ln x dx. Then I'm going to bring this plus 2 integral x squared ln x. Okay, and that's then equal to, what's left here is x cubed ln x minus 1, and minus this minus and this this minus sign and this minus sign here will multiply, and that will become plus 2. So this will be plus 2, and the integral that remains is just x squared dx. So now if you look at these two, these are dx here. These are the same thing, so that this will just become 3. So it'll become 3 times the integral of x squared ln x dx is equal to x cubed into ln x minus 1 plus 2, and then we have x cubed over 3. And now what we'll do is we'll bring the 3 across, so that means we'll end up with x squared ln x dx finally as 1/3 of this. So it's going to be x cubed over 3 ln x. So I'm going to write it in the same way. So x cubed over 3 ln x minus x cubed over 3 plus 2x cubed over 9, and then we'll add the constant right at the end. So now if you look at this, basically this will just become simplified to x cubed over 3 ln x minus minus here, this will be minus 1/9 x cubed plus c. So if you see, the answer is the same, but look at the effort required and the amount of work required to do it. So this is something quite important that you need to practice, because had you gone, your intuition would be correct. This would work, as you've seen here, and so does this. But you can see this how short this is, in fact, and how long this one matches. So just some food for thought for you as we progress through integration by parts. In the next video, we'll continue with some more examples. Thank you.